Yeah. So, like Dr. Killen said, we're just going to continue to talk about photoluminescence. So kind of the main idea here is basically looking at how charge will relax and how the holes, I guess mostly just the excited electron will relax, and the probabilities associated with that. So first we have to worry about when that relaxation is actually going to emit a photon, or radiative recombination. From Will's presentation, we can easily tell that the rate that this will emit is just going to be the Einstein coefficient. And we're just going to relabel that as Kr. And then also here's the equation for the oscillator strength, in case you want the equation. To simply just get the value of the oscillator strength, we can run the oscillator strength file, which is the same process we would do when we're calculating the absorption spectrum. And that will give us a big oscillator strength file, which will tell us this number for all combinations of bands that we're concerned about. Here we can also see different route commands that we can do on that oscillator strength file to get the different oscillator strengths that we might worry about. So we have oscillations between two excited states or intra-conduction band transitions. Same thing for the valence band transitions. And then we also have interband transitions. So basically going from an excited state to a relaxed state, I guess. And down below, we can see what one line of the oscillator strength file is going to look like. The two values that we're really concerned with are the oscillator strength and the transition energy, which both show up in our calculation of the radiative emission rate. The other pathway that charge can relax is going to be through non-radiative. And the way it will lose energy, instead of is through a photon, is through a phonon, or just heat that gets released into the rest of the system. And this is what we were calculating before when we were calculating the Redfield tensor. And so it will follow the exact same process that we did before, where we'll just use the autocorrelation functions and get the triple R matrix. And that's going to be approximately equal to the non-radiative rate. And just for an example, down below, I did this calculation for one of my models for the HOMO-LUMO transition. And when you run the correlation MATLAB script, the output in the triple R matrix is going to be inverse femtoseconds. In case you need to convert that to anything else. Combining those two rates, we're going to be able to get this photoluminescence quantum yield, which is a lot of words, but basically all it's saying is how many photons are emitted as a fraction of how many photons are absorbed. The big assumption that we make when we're calculating this is called Kasha's rule, which down in the bottom corner is a good kind of explanation of it. We assume that if you have an electron go to a very high excited state, far above LUMO, that it will descend to the LUMO state just releasing phonons, so non-radiatively. And then the only transition that will release a photon is between the LUMO and the HOMO. This doesn't happen all the time, which I'll talk about in a second. But this will greatly simplify this equation over to the left into what it is. If you are concerned about photon emission from higher excited states, this equation will become much more complex. As an example of some of these values, you can see down in the corner that I calculated for a few of my models. The first model has about a 55% quantum yield, so about half of the photons that are excited, or half of the electrons that are excited will release another photon. And as defects are added into it, COH and SiOC, that quantum yield goes down by quite a bit. So we also have some exceptions to Kasha's rule that we have to worry about. And I basically outlined basically how we would get these exceptions, but basically what it's playing with is if you want to adjust what KR, KN are in order to get emission from a different level. So for example, if you have a bunch of high excited states, even further above LUMO, they'll have a low overlap between LUMO and those higher excited states. So those electrons won't get a chance to fall down to LUMO. And instead what they might do is basically fall all the way down from a high excited state down to HOMO and release a photon that way. And so through like these two sorts of exceptions, we could get luminescence from different states and different energies than just the HOMO-LUMO gap. So it's something to pay attention to if you have like an odd band energy diagram, I guess. That is what I have so far.
Okay, question. Thanks. Any questions? Okay.
What is a phonon?
So the phonon is just a like discrete it's kind of like a photon, except instead of releasing into like space, it's just released into the surrounding atoms as heat. So it'll just vibrate all of the atoms next to it.
So it's really just energy being released?
Yes, into kinetic energy. Yep. Okay.
Quantum of sound?
Yeah, that would be a good way to put it.
How do you calculate the R?
The K, so Kr will be calculated through the Einstein coefficient that we were just talking about with Will before, which will involve the transition energy between these two states and the degeneracy, as well as the oscillator strength. The KNR, so the non-radiative, would be calculated through the non-adiabatic couplings that we were doing, calculated on the Redfield tensor with, and then just looking at the indices of that matrix, that would tell you the rate between those two states.
Why not choose when you HOMO to LUMO plus N transition? Why not LUMO minus N?
Like in this example, why I chose the HOMO-LUMO.
That last. Yeah, why you are concerned on HOMO to LUMO plus N?
Oh, yes. So here what I was trying to show was that the Kasha's rule, we're not always going to get photons only emitted from the HOMO-LUMO transition. We might get photons emitted from a HOMO to LUMO plus 5 or something like that. So I guess like a good example, a better example is this one off to the right, where the LUMO is very close in energy to all of these higher excited states. So if you put a photon up to this higher excited state, and LUMO is going to have like a relatively low oscillator strength connection to HOMO, the Kr is going to be low because its oscillator strength will be low. So then we will be about just as likely to see a transition from HOMO to LUMO releasing a photon, as well as like a higher LUMO state releasing a photon. Yep.
Questions? Let's check if anyone asks some questions in the chat line.
Yeah, so do you have a question in the chat line? How to assess if Kasha or non-Kasha transitions play a more important role? Can it be done visually? I think that a visual way to do it, other than being able to look at, I think a good first step might be to look at the band energies, kind of like a diagram that I have here. Another good way to do it might be through the emission spectrum, like what Sarah was showing before, where instead of just emitting photons for the HOMO-LUMO transition, we also had different energies that were releasing photons. So I guess you could cross-reference the emission graph with its peaks to the transition energy between different pairings of HOMO and like LUMO plus N.
Is sufficient justification to compute spectra and waste them in your next presentation?
I think so.